Okay, for background project, this airport, originally known as Pangkalan Cepa Airport, the facility was converted from a Royal Air Force base into a civilian airport. In 1999, the government initiated plans to relocate the terminal, leading to the construction of a new building complete in June 2002 at a cost of approximately RM55 million. In 2021, WCT Holdings Berhad was awarded RM440 million contract by the Ministry of Transport Malaysia to undertake the extension and upgrading of Sultan Ismail Petra Airport. There are two phases for this redevelopment. Phase 1, complete in May 2024, included a new terminal building. For second phase, it began immediately after the old terminal was vacated. This phase aims to further expand the airport's capacity and facilities. For future plans, in May 2024, Prime Minister Anwar Ibrahim announced that federal government's agreement to extend the runway by 400 meters, bringing the total length to 2,800 meters. This extension aims to upgrade this airport to international airport status, facilitating direct flights for Hajj pilgrims from Kota Baru to Jeddah. So since this airport using flexible pavement, so what is flexible pavement? It consists of multi-layered structure. The base layer is prepared subgrade, followed by a granular layer, and finally a top layer of asphalt. The structure is designed to flex and bend under the weight of aircraft, distributing the load through the layers beneath. It's more adaptable to the weather and is easier and faster to repair with a curing process that minimizes runway downtime. Main method used in construction. The construction process begins with site clearance. This involves removing vegetation, debris, or any existing structure to prepare a clean surface for construction. Next is setting up, which is essential to ensure that components like runway, taxiway, aprons, drainage system, and lighting are built accurately according to the design layout. Next is following that we have earthwork. This phase include cutting, filling, leveling, and compacting soil to form a stable subgrade, the foundation layer for our pavement structure. Once earthwork is complete, we move on to the runway construction phase, which include 4 major systems. The first one is drainage system, critical to prevent water accumulation and ensure the longevity of the pavement. The second one is flexible pavement. This is layered structure made as per material that absorb aircraft load. Third one is Airfield lighting system, installed for safe aircraft operation during night or low visibility condition. And the last one is Airfield system, cover operational infrastructure including marking and navigation aids. After the construction is complete, friction testing is conducted on the runway surface. These tests ensure that the runway provides adequate grip for aircraft, especially during wet conditions, to meet safety standards. The runway is constructed using a series of layered material. Surface course, made of a hot mix asphalt or HMA for a smooth and durable finish. Binder course, asphalt concrete with a larger aggregate that support the surface course. Base course, crushed aggregate or asphalt treated material that spread loads. Sub-base course, granular or cementary base to provide additional strength. Subgrade, the compacted soil layer at the very bottom, which may be stabilized with additive if necessary. Each layer plays a key role in ensuring the runway strength, durability, and resistance to heavy aircraft load. Standard follow. In Malaysia, airfield construction is governed by 2 main sets of standards. Civil Aviation Authority of Malaysia, or we call it CAAM. They enforce regulation through the Civil Aviation Directive (CAD), covering design, material, safety, and operation. For the International Civil Aviation Organization (ICAO),
As a member, Malaysia followed Annex 14, which provide global guidelines for runway design, dimension, pavement strength, and safety zone. This standard ensure that the airfield meet both national and international safety and performance requirements.
Next, I will be presenting about issues and challenges from site investigation to completion. Pangkalan Cepa Airport faces significant soil problems because it is built on soft marine clay and peat, which have very low bearing capacity and are prone to long-term settlement. This affects the stability of runways, taxiways, and building foundation. The high groundwater table further complicates excavation and drainage, especially during construction. Additionally, the airport is located in a flood-prone area, where heavy monsoon rains cause waterlogging, erosion, and further weaken to the soil. To address these challenges, engineers must implement ground improvement techniques such as piling, soil stabilization, vertical drains, and well-designed drainage system to ensure the airport's safety and long-term functionality. Second is material and design problem. At Pangkalan Cepa Airport, unsuitable construction materials deteriorate quickly due to high moisture and salinity, causing concrete spalling, corrosion, and asphalt wear, which increase maintenance and shorten infrastructure lifespan. Poor soil conditions require costly ground improvements and specialized design to prevent cracks and settlement. The flood-prone flat site makes drainage design difficult, risking waterlogging and safety hazard. Meeting strict ICAO standards adds further complexity, while rising material costs and supply chain disruptions strain budget and timelines, forcing adjustment in materials and construction planning. The next issues and challenges is heavy aircraft load. At Pangkalan Cepa Airport, weak and compressible soil struggles to support heavy aircraft loads, causing pavement deformation, rotting, and cracking, which require frequent repairs. Repeated takeoff and landing accelerate fatigue on runways, taxiways, and aprons. Stronger pavement design with thicker asphalt layers, reinforced subgrids, and proper load distribution are needed. Tough, they increase construction costs. Without this measure, heavy aircraft will shorten infrastructure lifespan and affect safety. Next is environmental issues and costs. Pangkalan Cepa Airport faces environmental challenges like flooding, soil erosion, and water pollution due to its proximity to rivers and coastal areas. Construction risks distributing sensitive ecosystems such as mangrove and wetlands, requiring careful environmental management. High groundwater levels complicate dewatering and raise contamination risks, while extensive draining soil treatments and safeguard increase project costs. Rising material prices, fuel costs, and supply chain disruptions further strain budgets, making it difficult to stay on schedule and within budget.
So for the next slide, for technology and innovation that used in this construction, the first one is the geosynthetics, used to strengthen a weak subgrid and enhance load distribution beneath the flexible pavement layers. The second one is the recycling methods. This also facility was constructed using reclaimed asphalt pavement RAP. For second, environmental protection methods, starting from the efficient drainage systems. By preventing water build-up beneath the runway, proper subsurface drainage shields the tarmac from structural collapse and lessens erosion around the airfield. The second one is the dust control measures. Water spraying and covered trucks minimize dust pollution during construction. For the conclusion, an important improvement in Malaysia's aviation infrastructure is the renovation of Sultan Ismail Airport in Pangkalan Cepa. The project intends to meet the needs of contemporary aviation while improving safety and sustainability through the use of flexible pavement design to respect site operation and cutting-edge technology in geosynthetics and recycled materials.